All right, so now that we extracted the file, the last part of it to complete the machine learning pipeline will be to analyze our data. So to do that, I've already opened up Weka here. So I'm just going to go ahead. I'm going to click on Open. I'm going to select all files. And then I'm going to navigate to the desktop, which is where I have what we just did. I have the PCAP converter. That's what we were doing. And this was label feature IOT CSV was my feature vector. So we took the PCAP files, 5 classes, and then we have this file. So I open it, and you can see it here. Here it is on Weka. We have a lot of information that's very valuable, right? So Weka tells us that we have 13,138 instances. We have 9 attributes, which include the label, so there's basically 18 features. So we can analyze statistics about the data just by clicking on all the individual ones. Notice this is the label, and if we click on the label, we can see TCP miscellaneous, camera, assistant, outlet, mobile. It actually gives us a histogram of the count. So it seems like this is an imbalanced data set, right? There's very few of the mobile category, and there's a lot of the camera. So there's a lot of cameras, not that many. And then assistance is like 2,000, so it's the second highest. All right, and so that's it. This is our, we went from raw data to a file in the vector space model that can fit into Weka, sklearn, and TensorFlow. The last part then is we want to do the classification. The labels, notice that the key thing is to check everything else can be numeric or nominal, but it's important to check that the label is actually nominal. So in this case, you can see that here it is nominal, so that means that it's a classification problem with 5 classes, at least according to Weka. So now I'm going to click on the Classify tab, and I can go ahead and select a couple of algorithms. So I'm going to go to naive Bayes. Now, before I do that, though, I need to select the label, right? And so I'm going to go here on the drop down and make sure I click on label to tell it that that's the target that we're trying to predict. And now the classifier should be highlighted, so I'm going to click on Bayes, select naive Bayes, for instance, and I'm just going to do like, a percentage split. So I'm going to do like 70% split, hit start, and there you go, right? So I ran my naive Bayes algorithm, and now I have my data. So you can see here we have the metrics, precision, recall, and F measure, and the F measure is really good actually for some of these, not so good for the miscellaneous category. So the miscellaneous category does not seem to be very, very good here. So you can see miscellaneous is 56.3, and then we have for the F measure. So the F measure for miscellaneous is one of the worst. Also for mobile is not great, but it's really good for camera, assistant, and outlet. All right, so as you can see, unlike the other problems that we've done before, right, where we did like iris and MNIST, and it was always 100% for everything almost, here this is a more realistic data set. As we can see, with the previous data sets, iris and MNIST, it was very academic problems. They were very easy. This is a more realistic problem. And it basically, you can see that it doesn't do well, actually, if you want to be honest. It doesn't do well for mobile. It doesn't do that well for miscellaneous, but it seems to be good at predicting, like for camera, assistant, and overall, though, notice that here's another point that I want to stress. Overall, the precision, the recall, and the F measures are above 90%. And so what does that mean? How do you interpret that? So this is an important concept. It's because it's a little bit misleading, right? So if you look at just the overall, you say, oh, it does 90%. And so everyone's happy and everyone thinks everything did great. But actually, it's over 90% for those metrics, precision, recall, and F measure, but overall only. Once you start digging into the specific devices, then you see that 3 devices it seems to do really well, and then 2 devices it doesn't do that well. And so that's why when you do your analysis, you actually have to dig in a little bit deeper. And that's why it's not enough just to look at the overall, but you should also look at the individual things. Now, remember that naive Bayes, if you want to remember, go back to the lecture on naive Bayes. It's only a baseline algorithm. It's meant to be really fast, and it's meant to be, the worst performance. So hopefully other algorithms will do better. Now, additionally, we should look at the confusion matrix here, and we can see that in the confusion matrix, maybe we should select like miscellaneous. You can see that miscellaneous is actually out of 382, or the test set, whatever it is, I don't have the number. Out of the test set, it only correctly classified 182. And there's 11, 59, and 18 samples that were incorrectly classified. So that is to say, it took all the samples, only 182 it recognized as miscellaneous, the rest it recognized as other things. For instance, it confuses miscellaneous with class C, which is assistant. So sometimes you may have some devices, these miscellaneous devices, that may be acting a little bit like assistants, and so the algorithm was not able to pick that up. That's why the confusion matrix is really important. Now, another thing here is in the camera, for instance. So the majority of the camera were correctly classified, and there were only 2 misclassifications, A and C. So it thought that cameras could be miscellaneous or they could be assistants, right? And then down here, for instance, we have one example of no misclassification. So look at D. So in D, outlet is correct. All outlet examples or samples are correctly classified as outlet, D. And there were 0, 0, 0, and 0 misclassifications. All right, so this is a very important point. All right, now let's try another algorithm, one more. So I'm going to do decision trees. So I'm going to go to trees, and I'm going to select J48. Still the same label, still 70% split. I'm going to apply it, yes. Now if we look at the output from decision trees, we were lucky that it ran, we can see that it does much better. So decision trees actually gets almost perfect precision, 100% or above 90, recall the same, F measure the same. So the decision tree algorithm has certainly done much better than the naive Bayes algorithm. And we see this here. Look at this diagonal, it's practically perfect. There's only 2 misclassifications here and 4 misclassifications here. And so this is a great example, actually, of a more realistic data set, right? So we had, overall, it's good, although it's not very good at predicting 2 classes. We also saw examples of how this data set is much larger. We start to run into big data memory issues. And then also we saw that naive Bayes is fast, doesn't require that much memory, but it's not that great, whereas decision tree did almost perfectly for our test set. The last thing I want to show is the select attributes option. So here the question might be, okay, as a cybersecurity professional, I'm interested in knowing, what features were the most important in determining what type of IoT device this was. And so to do that, I go to select attributes, click on choose. I'm going to select ranker, click on yes. It selects information gain, which is the method that it's going to use. Then I'm going to say use the full train set. I'm going to also specify that the label, the target, and then I'm going to run. So to predict that, I'm going to hit start. And now it gives me a list of the most important features. All right, so that's a list of the most important features. So I can also do cross-validation, repeat this. I'm just going to select the predict label, right, with ranker and information gain. I'm going to hit start, wait for it, and this is going to give me a list of the ranked features. Of the 19 features in the feature vector, I now have an ordered list that tells me basically, which ones are the most important. So obviously it ranks them from most important to least important. So actually here it's saying these last three are unimportant. So because they have a 0 value. So protocol, IP header length, and TCP urgent pointer are actually unimportant. Now that makes sense because protocol is what? Protocol is 6, and it means it's TCP and all packets were TCP. And so obviously when everything is the same, that doesn't tell you anything about differences, right? Remember that what machine learning looks for is the differences between the values of a feature. And so all the values, the value was 6 for this field, right? For protocol, it was all 6 for all packets. And so it's basically saying here, you know what? It's 0 contribution, get rid of it. Now, we can also look at the top, let's say 5 or 6 features, and we can see that according to this, the source port is actually the most important feature to determine if what type of IoT device this is. That is followed by the TCP checksum, window size, IP checksum, and so on. Sequence number, ACK number until here. So that's pretty interesting and pretty useful. So at this point, a cybersecurity professional might actually start digging into the why of this, right? So start looking at the network, start to understand certain aspects that the definitions of why ACK number and sequence number, why are those contributing features? So when my students did this, they had this theory, right, that sequence number and ACK number should be random numbers, right, in theory, but sequence numbers and ACK numbers are dependent on the size of the amount of data that has been transmitted, right? So the amount of data that you send from one point to the other. So you send a lot, and the sequence number might grow, or so the next sequence number might be a bigger number. So usually it's like you have this sequence number, the next sequence number is the previous one plus the length of the amount of data sent. So they were maybe as they're brainstorming. You might say, oh, it's because a camera sends a lot of data because it's, images. Whereas something else, like a power outlet, is just sending very little data, something about its status, etc. And so, this is where you start to make theories about what's going on. And this might be very useful for cybersecurity professionals. So anyway, in conclusion here, we looked at the selected attributes tab. And we ran 2 algorithms, naive Bayes and decision trees. We saw that decision trees did really well for the classification. Then on the selected attributes, we ran ranker, and with information gain, it ranked all the features from most important to least important. We saw that protocol is not important, and we saw that the most important features seem to be source port and TCP checksum. That basically completes the analysis in Weka. All right, so in summary, this was the IoT device detection lab, so Internet of Things. So we went through a more realistic data set, right? So more realistic data set. We saw many issues related to a more realistic data set, right? So we saw issues of big data. We saw how to take raw data and convert it to the vector space model, right? So we saw that. And then we saw basically a complete pipeline on ML, which included, feature extraction and the analysis via Weka, right? To the point where we could draw some conclusions, etc. So, this is a very important thing. As a system administrator, you might want to identify what are the Internet of Things devices that are being connected to your network, because as we all know, these Internet of Things devices are fairly new, which means that they're not as robust in their software. So the software assurance might not be there. They might be subject to vulnerabilities, and therefore the first step would be to identify these devices. So the goal was to build a machine learning algorithm that just based on the packets, what are the features that we need to look for in a packet that can allow us to detect if this is a IoT device, for instance. So in our particular case, we weren't classifying between IoT and non-IoT, we were more classifying among 5 IoT devices, right? So, but if you wanted to extend this to say as a project for your course, you could take the data that I provided, right, and then just extract all the packets that were IoT related versus all the other ones and build a 2-class problem, IoT, non-IoT. And it should be pretty similar to what we did, the code and everything. So that concludes this lab. So that, so that's the end of this lab. Thank you.